All right, today we're going to talk about one of the coolest and honestly most powerful shortcuts in all of vector calculus, Green's theorem. If you've ever stared down a really gnarly problem and just wished there was an easier way, well, you're in exactly the right place. Let's dive in. So to really get why this theorem is such a big deal, we first have to appreciate the kind of, frustrating problem it was designed to solve. And it's a problem that pops up all over the place, from physics to engineering. Just imagine this for a second. Let's say you have to figure out the total effect of a swirling wind on something moving along some crazy looping path. You'd have to measure the wind's push and pull at every single tiny point along that whole journey, and then add it all up. That sounds awful, right? Incredibly tedious. Well, there's a name for that process. It's called a line integral. You're basically adding everything up along a one-dimensional line, even if that line is twisting all over a 2D space. And if that path is complex, forget about it. It can be an absolute nightmare to calculate. But what if I told you there's a way to get the exact same answer without ever having to walk that complicated path at all? And this is where the pure genius of Green's theorem just shines. It gives us this brilliant, almost magical connection between what's happening on the edge of a shape and what's happening all over the inside of it. Okay, so on one side of the equation, we've got our line integral. This is, let's be honest, the hard way. I want you to think of it like walking the entire fence line of a huge, weirdly shaped property and having to measure every single foot of it. But on the other side, we have something totally different, a double integral over the entire area inside that fence. This is the shortcut. So instead of walking that whole fence, you just get a bird's eye view of the entire field. And what you're looking at is something called the curl. It's basically the sum of all the tiny microscopic little swirls of energy at every single point inside that field. And this is the core magic of the theorem right here. Green's theorem says that the long, tedious line integral around that closed loop is exactly equal to the much easier double integral of the field's curl over the area inside. It turns a hard boundary problem into a much simpler area problem. This is the main takeaway. It's a total shift in how you look at the problem. The total effect you feel on the boundary is completely dictated by the sum of all those tiny little rotations happening everywhere on the inside. Okay, that sounds amazing in theory, right? But does it actually work? Let's put it to the test with a simple example straight from the source material. So here's the plan. We're going to take a simple square path going from the origin out to a point AA. We'll do the calculation both ways, the long way and the shortcut, and see if we really do get the same answer. First up, the hard way. This means we have to do 4 separate calculations, one for each side of the square. We go along the bottom, then up the right side, back across the top, and finally down the left side. And then we add all 4 of those results together. It's definitely a bit of work. And now for the shortcut. We just set up one single double integral over the whole 2D area of the square. It is a much, much more direct calculation. And check this out. This is the payoff. Look at those results. The line integral, the hard way with 4 separate parts, gives us a cubed over 2. The double integral, the shortcut, gives us the exact same thing. It's not an approximation. It's not close. It is a perfect match. The theorem works. So this is super cool for 2D shapes. But the really profound thing here is that this isn't just some clever math trick for flat planes. It's actually a peek into a much deeper, more fundamental principle in the universe. You can think of Green's theorem as the flat 2D version of a much bigger idea. This core concept, that what you measure on the boundary of a space is directly related to what's happening inside that space, it holds true in higher dimensions too. When you move up to 3 dimensions, this idea is called the divergence theorem. It basically says that the total amount of stuff flowing out of a 3D shape, we call that flux, is equal to the total amount of stuff being created at every single point inside that shape. It's the same beautiful idea, just bumped up a dimension. So why should you care? Beside helping you on a math exam, where does this actually show up in the real world? What's the real power here? Well, it shows up pretty much everywhere. In aerospace, it's used to calculate the lift on an airplane wing. In engineering, it helps figure out fluid flow through pipes. It's absolutely fundamental to understanding electricity and magnetism through Maxwell's equations. There's even a clever mechanical device called the planimeter that uses this principle to let you trace any weird shape, and it automatically tells you the area inside. When you boil it all down, the true power of Green's theorem is the beautiful bridge it builds. It tells us that if you want to understand some big, large-scale property that you can only measure on the edge of something, well, you can figure it out by just adding up all the tiny, local behaviors happening everywhere on the inside. And that leaves us with a pretty cool idea to think about, doesn't it? Green's theorem shows us how a problem that seems almost impossibly complicated can suddenly become simple, just by looking at it from a different angle. It really makes you wonder, how many other huge challenges in science or even just in life are just waiting for us to find their own elegant shortcut?